So the figure shows a connection that has 3 grade 4 bolts. The tensile shear load on the joint is 500 pounds force. So this means we've got 5,000 this way and 5,000 this way. The members are cold drawn bars of AZ 1020 and find the factor of safety for each possible mode of failure. So I don't think we have time to plug in all the numbers, but we can at least figure out what number, what we need to know. So this here is just, this 823 in your book is the diagram to look at when you're solving these problems. And the first figure just shows you the situation it's talking about. The second figure is this moment loads. This could happen here, right? I think in the example I showed, it's possible for this joint to come apart like that, but it's unlikely because there's 2 bolts that are spaced here. And also, this is really difficult to analyze. So usually you just bump up your factor of safety. Your factor of safety is higher on all the rest, then you're probably okay. So this Shigley ignores. All right. This situation, this is the bolts shearing. And the bolts will shear if the shear stress in the bolts, and now actually, how do I know that this is a shear, right? This plane that the bolts shear on or the bolts fail on, this is the plane that we're talking about. And the surface normal is in this direction, and that's perpendicular to the applied load. So that means we're going to have a shear stress in the bolts. The shear stress in the bolts is that force divided by the area of the bolts. And what area should we use? We're going to assume that the bolts have the threads not in the shear plane. So we're going to assume that it's the full diameter of the bolt. If it's a properly designed joint, you're not going to have threads on this purple plane where the bolt's going to shear. So this is going to be A sub D, where D is the major diameter of the bolt. Now, how many bolts do we have acting? This is the area for a single bolt in shear. We've got 3 bolts acting. So our stress is going to be that force divided evenly by 3 bolts acting over an area that's, well, AD is pi times the diameter of the bolt squared divided by 4. We've got 1/4 inch bolts, I think. Yeah, 1/4 20 UNC. So pi times 0.25 squared divided by 4. We've got 0.049 inches squared. So our shear stress is 5,000 pounds, 3 times 0.049. We've got 33,953 PSI. So that's actually pretty high. Now, our safety factor is how many times could we increase we're going to use von Mises stress before we yield, right? Because the von Mises failure criterion says you yield when the von Mises stress is equal to the yield strength. We're going to say how many times could we increase the von Mises stress before we get to yield. Now, we've done this before with welds, okay? So I'm going to skip right to the answer. If you were to figure out what the von Mises stress is when you've got pure shear, you're going to find in the formula that you've got a √3 times your shear stress. So that √3 ends up on the other side. Our factor of safety is 0.577 times the yield strength, or 1/√3 times the yield strength divided by tau. Okay? And keep in mind, I used yield strength. So I messed up in one of the videos, and I kept on I think in one of the videos about the bolts in tension. When your bolts are in tension, you always use the proof strength. When your bolts are in shear, you're going to use the yield strength. So it's a little bit different. So let's take a look at grade 4 bolts. Grade 4 bolts. the minimum yield strength is 100 KSI. That's actually pretty high. Okay, so this is 100,000 PSI. So it looks like we're going to have 57,700 PSI divided by 33,953. We've got a factor of safety of 1.7. So we're okay there. All right, so this is good. That's case C. Let's look at case D. D is the whole member rupturing, right? This is this thing rupturing due to a tension load. How do I know it's a tension, or how do I know it's a normal force? The plane that we're talking about at breaking is here. That is, the normal to that is parallel to the applied load. So we're going to have a normal stress. We're going to analyze this as though there were a normal stress that was even across this whole area. Now, in our case, our planes are either here or here. Which one of these is more relevant to us? All right, we were on part D, and we had just shown that it's going to fail across one of these two areas, and we were asking which of these two places is it going to fail? Well, it's probably going to fail at the one with the smaller cross-sectional area. That's where the stresses are going to be greater. So it's going to be failing here because there are two bolts that are removing material from this 2 3/8 inch wide section. So it's certainly not going to fail here, right? Because that has the full area. This one has a 1 hole cut in it. This one has 2 holes cut in it. So let's find the area of that, and we'll figure out what the stress is, the force divided by the area, and we'll see what our factor of safety is. And you might need to consider the fact in some problems that the thicknesses of the two members might be different. Or the widths of the two members might be different. In this case, it's symmetric. It doesn't really matter which one we analyze. We'll just see if it fails in one of the two. All right, so D, oops. This is failure mode D given in Shigley's figure 823. We've got a 2 3/8. Our area that we're going to consider, one of these planes, is 2 3/8 inches minus 2 holes, and each of them is, we're going to approximate them as 1/4 inch because it's a 1/4 inch bolt. So 2 3/8 inches minus 2 bolts. Each of them we're saying has a clearance hole of 1/4 inch. Now, if we wanted to be more careful, and if this factor of safety were, right on the line, we might want to reanalyze. You might look up online. I'm going to look up clearance holes for, we got a 1/4 bolt. And so you're going to find some clearance hole sizes. For a close fit, a clearance hole for a 1/4 bolts, you should use an F drill. That's about 0.257, right? It's very close to a 1/4 inch, but it's a little bit bigger. So we're just going to use a 1/4 inch for now for calculating that area. Our area is, this is one dimension of our area. And the second dimension is, we're talking about it failing, along this plane. So we need to think about the thickness, 5/16 inch. All right, so 5/16 times 2 plus 3/8 minus 1/2 inch. I get 0.586. 0.5859. All right, that's our area. Now our force is the 5,000 pounds, and it's the whole 5,000 pounds, right? It's not like these two areas help each other. It could fail here, it could fail here, or it could separately fail here. This is the one with the smallest area. They're all seeing, well, actually, you need to think about that. Let's be a little bit more careful here. If you were to flip this around, right, if you were to look at the light pink part, let's pretend that this is the light pink. Well, on the light pink part, you're not going to have this boundary here. Oh, I'll just draw over it. The light pink part actually has its edge here. So we're analyzing this one. And I think for this one, you can safely say that the full tension of 5,000 pounds acts here on this area. So I think that you can safely say that the full 5,000 pounds, but just think about it. Is the full 5,000 in this member, is the 5,000 pounds going to be acting on this one? No, it's going to be reduced somewhat after it gets past these bolts. These bolts are going to be taking up some of that load. And so you could kind of get the idea of a tension diagram, and it's changing depending on where it is. But for our problem, it's easier. We've got 5,000 pounds acting across this smaller area. And since the two parts are the same area, then it doesn't really matter. So let's go ahead and find 5,000 pounds. All right, so the stress, it's a normal stress because the area that we're talking about is in the same direction. The normal to it is in the same direction as the applied load. Same direction. So we've got a sigma, that's F over A. 5,000 divided by 0.58. And we've got 8,533 PSI. And what's our factor of safety? Well, N times sigma prime equals SY, but sigma prime is really equal to sigma, so we can just get N is equal to SY over sigma. Now, what is the SY that we should be using? It's not the yield strength of the bolts anymore. It's the yield strength of the member. The member is AZ 1020. So for AZ 1020, SY is equal to 57.7 KSI. So 57,700 divided by sigma. Oops, I'm sorry, that's not right. It is not that. For AZ 1020, oh, it is 57 though. Wasn't reading properly. Let's go ahead and look it up in the book. That's a good idea. As opposed to looking what's already written down. Oh, it's 18, is it? 20? Yeah, here we go. 1020, cold drawn, 57 is the yield strength. Okay. Cold drawn, 1020, 57. Great. So 57,700 was very close, but it's 57,000 over 8533. Get a factor of safety of 6.68. Okay, E. Now we're looking at bearing on either the bolts or bearing on the material. The bolt is usually the stronger material, so really we only really need to look at the bearing stress in the bearing failure in the members, because it's the same stress on either one. the bolts are just going to have a higher factor of safety. So we don't really even need to analyze that. Okay, but let's look at what sort of area are we talking about? Well, it is the projected area of this cross section. We say, all right, even though it's going to be a bolt contacting on the lower edge here and pressing up against the material and making that fail, instead of modeling that curved contact, we're going to say, let's pretend that the force that's on that bolt is acting over an area that looks like this in this plane. So in our case, it's like, let's analyze just one of them. It's the area of the bolt. And then in this cross section, it's also got the same thickness, right, as the part, 5/16 inch. All right, so it's got the diameter of the bolt and the thickness of the part. That's our area that we're talking about. So our area in this case is the diameter of the bolt times the thickness of the part. The diameter of the bolt, that was 1/4. Our thickness was 5/16, I think. 5/16. 0.078 inches squared. And we have 5,000 pounds, but it's not, well, let's think about it this way. Our stress, sigma, and it's a normal stress because this area is parallel to the applied load, or the normal to it is parallel to the applied load. So sigma is equal to F over, we've got 3 of these areas. We've got 3 bolts, so the bolts share those loads. 3A. 5,000 divided by 3 times that area is 21,000, 21.333 KSI. So our factor of safety is SY over that. And that's 57,000 divided by that number, 2.67. And finally, that's in the members, not the bolt. If we wanted to do the bolt, we could, fine, we can replace this SY with a 10,000 or 100,000. That's what the bolt was. So I guess I can do that really easily. The bolt factor of safety is like 4.69, but it's higher, so we don't really care. F, we could have shear tear out. And I think in this case, well, there's 2, yeah, you need to consider again the 2 different parts. For this pink part on top, as it was originally drawn, the edge of the part was here. That was close to these 2 bolts. So you'd have 1, 2, 3, 4 places it would have to fail in order for there to be a tear out. But in this one, you have only got 2 places. 1, 2. On the other hand, I suppose you could say that the stress is you need to divide by the number of bolts. So it depends on how conservative you want to be. Do you want to assume that the full 5,000 pounds force is acting here, and that these shear planes are going to see a full 5,000 pounds? It's up to you how you decide to do it. Let's go ahead and be really conservative and say the full 5,000 pounds force we're acting on this bolt alone. In which case we probably would have to, that's not really consistent with our assumptions, right? We've already said that only 1/3 of the force is acting on this bolt in bearing stress. So yeah, I don't think it makes sense to be super conservative there. Let's just think that force acting over these 2 places. So each of those, we're talking about these areas. Let's draw the diagram. Here's the hole in the part. And what we really want is we draw an imaginary line here at the edge of the bolt, and we want this area and this area. So it's going to be the thickness of the part times whatever this distance is. That distance, in our case, each of those areas, the distance is whatever the distance from the center of the hole to the edge of the part is, minus half the bolt's diameter. So that's, see, how much distance do we have? 5/8 inch for either one, 5/8 inch. Minus half the diameter of the bolt, 1/2 of 1/4 inch, or really half the diameter of the hole. So you could be careful there. Let's calculate that times 5/16 thickness. Okay, this is 0.15625 inches squared. And this force, well, how much force is acting on this one? It's 1/3 of the total force, 5,000 divided by 3. That's what we assumed with the bearing stress calculation, so it only makes sense to divide by 3 here. 1667. And there's 2 areas that it's acting over. So our stress, is it a sigma or is it a tau? These areas have normals that are perpendicular to the direction of the applied load. So it's going to be a shear stress. Our shear stress is that force divided by 2 times the area we just calculated. It's 5,333 psi. Now it's a shear force, so when we calculate the safety factor, N is equal to, what do we have? 0.577 times SY divided by tau. So 0.577 times 57 KSI divided by 5.33 KSI. We got a factor of safety of about 6.167. And let's say that all of the force were acting over that area. Fine. Well, we've got 3 times as high force. We can divide our factor of safety by 3. We still have a factor of safety of 2. Our smallest factor of safety is that on the bolts. So it doesn't really even matter how conservative we are there. The bolts, assuming that they see the load evenly distributed among them, are what's going to fail first. And they're going to fail in shear. Before any of these other things happen, before we have tensile failure of the member, before we have bearing stress failure of the member or the bolts,